Chapter 3. Design of shell, head, and components. The shell is the primary component that contains the pressure. Pressure vessel shells are welded together to form a structure that has a common rotational axis. Most pressure vessel shells are cylindrical, spherical, or conical in shape. Horizontal drums have cylindrical shells and are fabricated in a wide range of diameters and lengths. Tall vertical towers are constructed in a wide range of shell diameters and heights. In this course, we will cover types of vessel design, design of cylindrical shell, types of dished head, optimum vessel size, tall vertical vessel, and skirt. References. Number 1. Rules for construction of pressure vessels, Division 1 ASME boiler and pressure vessel, Part UG. Number 2. ASME code calculation, cylindrical shell components, 2004. Number 3. ASME basic calculation, pressure vessel. Number 4. ASME Section 8, Division 1, Example Problem Manual. Number 5. PV Handbook V12, Eugene F. May GEC, Pressure Vest Publication, Inc. Number 6. PV Design Handbook, 2nd edition Henry Bednar, Krieger Publication. Number 7. PV Design Manual, 3rd edition Dennis Moss, Gulf Professional Publishing. Number 8. Guidebook for Design, ASME Sect 8 PV 3rd edition. James Farr, ASME Press. The design of pressure vessels and vessel parts shall conform to the General Design Requirements Part UG 16, in the following paragraphs and in addition to the specific requirements. For ASME code, the codes start from paragraphs UG 1 to UG 137. The minimum thickness permitted for shells and heads, after forming, and regardless of product form and material, shall be 1/16 inches. 1.5 millimeters, exclusive of any corrosion allowance. Types of pressure vessel. There have 3 types of pressure during design, such as design pressure, maximum allowable working pressure or MAWP, and operating pressure. Pressure vessel according to end construction. According to the end construction, the pressure vessels may be open of end or closed end. Pressure vessels according to dimensions. If the ratio T/D is less than 1/10, the vessel is said to be thin shell, and if the ratio is greater than 1/10, it is said to be a thick shell. Thin shell is for boilers, tanks, and pipes. Thick shell is for barrels and pressure cylinder. Maximum allowable working pressure, MAWP. From UG 98, page 117, it mentioned the requirements of MAWP. Pressure vessels must always operate at a pressure lower than their maximum allowable working pressure, MAWP. MAWP is defined as the maximum gauge pressure permissible at the top of the completed vessel in its operating condition for a designated temperature. Generally, MAWP will be higher than the design pressure because wall thicknesses are in discrete sizes and the designer will always choose a value greater than that called for. In the example, since it is unlikely that he can design for exactly 95 psi, the designer selects the next highest level, which, in this example, is 100 psig. Therefore the vessel's MAWP is 100 psig. Maximum allowable working pressure. Pressure vessels must always operate at a pressure, 95 psi, lower than their MAWP, 100 psi. The test pressure, 150 psi, for the vessel is generally 1.5 times design pressure or MAWP, 100 psi. MAWP, 100 psi, will be higher than the design pressure because wall thicknesses are in discrete sizes and the designer will choose a value greater. Burst pressure, 400 psi, will typically be in the range of 3.5 to 4 times MAWP, 100 psi. The pressure used in the calculations must be equal to or greater than the MAWP to be marked on the vessel nameplate and manufacturer's data report. A lower pressure which must be met for process conditions must not be used in the calculations. If the markings required are stamped directly on the vessel, the minimum letter size is 5/16 in. If they appear on a nameplate, the minimum letter size is 5/32 in. Internal pressure. Pressure vessels operate with internal pressures that are either above or below atmospheric pressure. They rely on the strength of their walls and flanges to prevent failure. Part UG45, mention for vessel under internal pressure plus corrosion allowance. Part UG27, mention the thickness of shells under internal pressure. This paragraph provides formulas to determine minimum required thickness of shells under internal pressure. Design pressure. UG21 states that vessels must be designed for the most severe condition of coincident pressure and temperature expected in normal operation. The code also states that the maximum pressure difference between the inside and outside or between chambers of a vessel during operation and test must be considered. Design pressure is the pressure used in the design of a vessel component together with the coinciding design temperature, metal temperature, for the purpose of determining the acceptable thickness and inherent details of the component. This should be below MAWP and based on company standards can vary from 10% to 25% above the maximum operating pressure of the system. Design temperature. Part UG20 established the requirement for maximum design temperature and minimum design metal temperature, MDMT.
The maximum temperature at any point shall not exceed the maximum temperature listed in the stress tables for the specification, or the external pressure chart, if the vessel is under external pressure.
The minimum design metal temperature marked on the nameplate must correspond to the greatest value of the maximum allowable working pressure marked on the nameplate. Design temperature for vessels under external pressure shall not exceed the maximum temperatures given on the external pressure charts.
Max, highest mean metal temperature expected in operation is 50 degrees Fahrenheit.
Min, lowest mean metal temperature expected in operation is -25 degrees Fahrenheit. Maximum allowable pressure, MAP. Part UG98 established the requirement for maximum allowable pressure. The term MAP is often used. It refers to the maximum permissible pressure based on the weakest part in the new, uncorroded, and cold condition, and all other loadings are not taken into consideration. The MAP is defined as the maximum allowable pressure of the vessel in the new and old condition. Pressure of fluid. Pressure and depth is the fundamental relationship in the oil industry. The easiest way to calculate pressure from depth is to use the pressure gradient of the given fluid. To find the pressure per square inch for any feet head not given in the table above, multiply the feet times 0.433. 0.433 is the gradient for pure water, Sg equals 1, static gravity, in imperial units, remember it. Example 1. Pressure of fluid. The pressurized tanks types can be of a spherical or bullet shape, and these storage tanks are used to store of fluids at pressures above atmospheric. The pressure, P of a water tank is 86 psi. The connecting pipe above the tank is 21 feet. Calculate the static head pressure and total pressure for the pressurized tanks. Calculate the static head pressure and total pressure for the pressure tanks. To find static head pressure. First method. 21 times 0.4333 equals 9.099 psi, from table. Second method. 0.433 times 20 feet equals 8.66. 1 feet equals 8.66 plus 0.433 equals 9.099 psi, if no table provided. Then, the total pressure, PT of the water tank is PT equals design plus PS equals 86 plus 9.099 psi equals 95.099 psi. Hydrostatic test. Part UG 99 established the requirement for hydrostatic test. Hydro test is the technique in which pipes, pressure vessels, gas cylinders, tanks are tested at required design pressure of the system or pipes or vessel to check the leak and strength. Hydrostatic test pressure is the pressure is at 1.3 times the MAWP or the design pressure to be marked on the vessel. Hydrostatic test pressure equals 1.3 times maximum allowable working pressure or MAWP. Example 2. What is the minimum hydrostatic test pressure for an existing vessel that is being re-rated using the design allowable stress, where the MAWP is 1000 psi and the allowable stress factor correction is 1.0? Test pressure equals 1.3 MAWP times S test temperature divide S design temperature equals 1.3 times 1000 times 1 equals 1300 psi. ASME 8 Division 1. The scope of 8-1 Division 1, Part UG 27, has been established to identify the components and parameters considered in formulating the rules given in ASME 8, Division 1. A simplified equation was developed by the UG 27 ASME Code 8 for determining the required thickness of a cylinder subjected to internal pressure. Longitudinal stress can govern the design of a cylindrical section when loadings other than internal pressure induce longitudinal stresses that are greater than 1/2 of the hoop stress due to internal pressure. Design temperature formula can be found in PV Handbook page 18-24. The following formulae, found in ASME section 8-1, paragraph UG 27, C, are used for calculating wall thickness and design pressure. Paragraph UG 31, A, states that these calculations are used for tubes and pipes under internal pressure. The non-pressure loads listed in UG 22 must also be considered, and, if necessary, the thickness must be increased or stiffeners and other means must be provided to prevent overstress. General Vessel Formula. SARS, Pressure Vessel Design Manual Textbook by Moss, page 16. The table summarizes the ASME code equations used to calculate the minimum required thickness for common pressure vessel components. Design of cylindrical shell. SARS's ASME code equations. The formula is used to design cylindrical shell, spherical shell, semi-elliptical head, tori spherical head and conical section in terms of thickness, pressure, and stress. The abbreviations from the formula. The symbols defined below are used in the formulas of this paragraph. P equals internal design pressure. R equals inside radius of the shell course under consideration. S equals maximum allowable stress value, see UG 23 and the stress limitations specified in UG 24. E equals joint efficiency for, or the efficiency of, appropriate joint in cylindrical or spherical shells, or the efficiency of ligaments between openings. T equals minimum required thickness. Cylindrical shell. UG27 mention, the minimum required thickness of shells under internal pressure shall not be less than that computed by the following formulas except as permitted in Appendix 32, Local Thin Areas. The ASME Boiler Code Section I, as well as Section 8, requires longitudinal and circumferential butt joints to be examined by full radiograph. In addition, provision shall be made for any of the loadings listed in UG22, when such loadings are expected. The code formulas for determining the thickness or pressure in a longitudinal joint, circumferential stress, of a cylinder when the thickness does not exceed 1/2 the inside radius or P does not exceed 0.385 SER. Circumference stress, longitudinal joints. T equals P times R divide S times E minus 0.6 times P plus corrosion. Or P equals S times E times T divide radius plus 0.6 times T. When the thickness does not exceed 1/2 of inside radius, or P does not exceed 0.385 SE, the formula shall apply. Longitudinal stress, circumference joints. T equals P times R divide 2 times S times E plus 0.4 times P plus corrosion. Or P equals 2 times S times E times T divide radius minus 0.4 times T. These longitudinal stress formulas are limited to use when the thickness is less than or equal to 1/2 of the inside radius or P does not exceed 1.25 SE. Spherical shell. A spherical shape is tough to manufacture, therefore more expensive, so most pressure vessels are cylindrical with 2:1 semi-elliptical heads or end caps on each end. When the thickness does not exceed 0.356 times R, or P does not exceed 0.665 times S times E, the following formulas for determining the thickness and internal pressure of a sphere shall be applied. T equals P times R divide 2 times S times E minus 0.2 times P, or P equals 2 times S times E times T divide radius plus 0.2 times T. Example 3. What is minimum thickness for a pressure vessel having a cylindrical shell with an inside diameter of 20 feet, an internal design pressure of 900 psi, made of SA516 grade 70. Normalized operating at 600 degrees Fahrenheit, with an allowable stress value of 17,500 psi, that was constructed with Type 1 weld joint and full radiography. Required variables. P equals 900 psi. R equals internal diameter divide 2 equals 20 divide 2 equals 10 feet. Equals 10 feet x 12 in equals 120 in. S equals 17,500 psi. E equals 1.0, 100% radiography. What is minimum thickness for a pressure vessel? To solve this problem, we should use T equals P times R divide S times E minus 0.6 times P plus corrosion. And the answer is 6.368 inch. Maximum allowable stress. Stress value, S, PG 191 PV Handbook. The maximum allowable stress values to be used in the calculation of the vessel's wall thickness are given in the ASME code for many different materials. Refer to example 3. Material type SA516, GR70, and operating temperature at 600 F. Stress value equals 17.5 x 1000 psi equals 17,500 psi. Efficiency. Joint efficiency is concept found in several API and ASME codes. Table UW12, PG7. It is a numerical value, which represents a percentage. Refer to example 3, Y joint efficiency, E equals 1. Refer to the table. Construction type, 1, weld joint. Testing type, full radiography. Example 4. A vertical boiler is constructed of SA 515-60 in accordance with the requirements of Section 8-1. Calculate the required thickness of the shell if the allowable stress is 138 MPa. Given. The inside diameter is 2,440 millimeters. The internal design pressure is 0.69 MPa equals 100 psi at 230 degrees Celsius. The corrosion allowance is 3 millimeters. The joint welding efficiency is 0.85. For circumference stress, P 0.385 SE. Thus, allowable stress equals 0.69 MPa 0.385 x 138 MPa x 0.85 equals 45.16 MPa. Then, 0.69 MPa, P, 45.16 MPa, 0.385 SE, or 100 psi, 0.69 MPa, 6,550 psi, 45.16 MPa. The inside radius R equals 1,220 plus 3 equals 1,223 millimeters. To solve this problem, we should use this formula. T equals P times R divide S times E minus 0.6 times P plus corrosion. The thickness must be less than 0.5 R equals 0.35 x 1,220 millimeters equals 610 millimeters. The answer is 7.225 millimeters, where the T equals 7.225 millimeters 610 millimeters. Thick cylindrical shell. Pressure vessels with inner diameter to wall thickness ratio less than 20 are called thick shell pressure vessels. These are used in high-pressure cylinders, tanks, and gun barrels etc. For thick-walled vessel. Example 5. Accumulators are used to store water under pressure and to take up expansion or contraction within hot water systems. They are charged with water from either the mains or from a pump system, and are capable of delivering extremely high flow rates until empty. Vessels should be sized to meet the maximum short-term demand to taps. Calculate the required cylindrical shell thickness of an accumulator with P equals 34.75 MPa, R equals 24.7 centimeters, S equals 143 MPa, and E equals 1.0. Assume corrosion allowance equals 3. Solution. Thickness is equals 70.351 and plus with corrosion 3 millimeters. So, the answer is 73.351. Example 6. Calculate the required cylindrical shell thickness of an accumulator with P equals 52.75 MPa. R equals 45.7 centimeters, S equals 138 MPa, and E equals 1.0. Assume corrosion allowance equals 0. The quantity 0.385 SE equals 53 MPa, 0.385 x 138 x1, is bigger than design pressure 52.75 MPa. T equals P times R divide S times E minus 0.6 times P plus corrosion. Since the corrosion is 0, the answer is 200. Design of head. The most common type of end closure for a cylindrical shell is a formed head. Paragraph UG32 contains the design requirements for formed heads subjected to internal pressure. Course overview.
Blank dished head. Semi-less full hemispherical head. Spherical head. Ellipsoidal head. Tori spherical head.
Contents of video for head design in VLE. Here are the videos for head design from VLE. Kindly please go through to the video for an additional information. ASME 8 Division 1. UG32 contains the design requirements for formed heads subjected to internal pressure. There are 5 types of formed heads: ellipsoidal, tori-spherical, hemispherical, conical, and tori-conical. Types of dish head. There are 6 types of formed heads: ellipsoidal, tori-spherical, hemispherical, conical, flat head, spherical head. Conical or tori-conical sections are also used as transition sections between shell sections of different diameters. ASME code design formula. General formulas should be used to find the thickness and pressure for dish heads such as ellipsoidal, tori-spherical, hemispherical, and conical. Blank dished head. Paragraph PG 29.1 stated, the thickness of a blank unstayed dished head with the pressure on the concave side, when it is a segment of a sphere, shall be calculated by the following formula. A.
Minimum thickness formula. Maximum allowable working pressure.
Min thickness of the piping. Not.
Here is the formula for blank dished head.
A. Minimum thickness formula. B. Maximum allowable working pressure. C. Minimum thickness of the piping.
Where T equals minimum thickness of head, mm. P equals maximum allowable working pressure, MPa. L equals radius to which the head is dished, measured on the concave side, mm. S equals maximum allowable working stress, MPa. E equals efficiency of the weakest joint used in forming the head. C equals corrosion allowance.
Example 7. Calculate the thickness of a seamless, blank unstayed dished head having pressure on the concave side. The head has a diameter of 1085 mm and is a segment of a sphere with a dish radius of 918 mm. The maximum allowable working pressure is 2500 kPa, 2.5 MPa equals 362 psi, and the material is SA-285A. The temperature does not exceed 250 C. 482F. Maximum allowable stress is 88.9 MPa. Given Y equals 0.4 and efficiency equals 1. State if this thickness meets code. The thickness of this seamless blank unstayed dished head is 26.89 mm. To check if the thickness meet the code, minimum thickness of the pipe should be calculated. Example 8. Calculate the thickness of a seamless, blank unstayed dished head with pressure on the concave side, having a flanged in manhole 6 in × 16 inches. The head has a diameter of 47.5 in and is a segment of a sphere with a dish radius of 45 inches. The maximum allowable working pressure is 225 psi and the material is SA285A. The temperature does not exceed 428 degrees Fahrenheit. The thickness of seamless dished head is 0.764 inch. Hemispherical head. Hemispherical tank heads are the strongest of the formed heads. They can resist about twice the pressure rating of an elliptical dished head or cylindrical shell of the same thickness and diameter. Due to their strength and resistance, these tank heads are widely used for the storage of liquids and gases under pressure. The required thickness of a hemispherical head is normally 1/2 the thickness of an elliptical head for the same design conditions, material, and diameter. The required thickness of a hemispherical head is normally 1/2 the thickness of an elliptical or tori-spherical head for the same design conditions, material, and diameter. Hemispherical heads are normally fabricated from segmented sections that are welded together, spun, or pressed. Hemispherical heads are an economical option to consider when expensive alloy material is used. Example 9.
A vertical pressure vessel has seamless ellipsoidal head at the top of the shell that is under pressure on the concave side. The head has an inside diameter of 4 feet, is made from SA387 grade 2, and operates at MAWP of 1000 psi and 900 F, where the allowable stress is 14,700 psi. What is the minimum thickness required for these conditions?
The minimum thickness required is 1.644 in. Example 10. Calculate the minimum required thickness for a blank, unstayed full hemispherical head. The radius to which the head is dished is 7.5 inches. The MAWP is 900 psi and the head material is SA285C. The average temperature of the header is 570 F. The minimum required thickness is 0.24 in. 2:1 elliptical head. A 2:1 elliptical tank head is fabricated to have a certain shape instead of a particular dish radius or knuckle radius. The dish radius is approximately 90% of the diameter and the knuckle radius is approximately 17% of the diameter. 2:1 elliptical flanged and dished heads are ASME compliant. The required thickness and pressure is mentioned in this slide. Example 11. To calculate the required thickness and maximum pressure for the head. An elliptical head has a design data as below. Calculate the required thickness and maximum pressure for the head. The required thickness is 0.116 inch. And maximum pressure is 216 psi. Tori-spherical head. Tori-spherical, or flanged and dished, head is typically somewhat flatter than an elliptical head and can be the same thickness as an elliptical head for identical design conditions and diameter. The formula for minimum thickness and pressure for a 2:1 ellipsoidal head is Example 12. A drum is to operate at 500 F and 350 sig and to hold 5,000 Gel. Dished tori-spherical heads inside radius is equals 78 in. The material is SA285 grade A. Assume S equals 11,200 psi and E equals 0.85. Calculate the required thickness. The required thickness of dished head is 2.547 inch. A dishing process of 1-piece heads. 1. Circular blank being removed out of the furnace once heated at the proper temperature. 2. Circular blank being transferred to the 2500 T hydraulic press by means of the overhead crane. 3. Circular blank being positioned onto the forming ring laying on the lateral transfer lorry. 4. Lateral transfer lorry being positioned within the operating area of the hydraulic press fitted with the forming die. 5. Circular blank being dished. 6. Dished head being extracted out of the forming tools.
Combination head and shell tutorial guideline. This lesson contents of guideline for Tutorial 1 and Tutorial 2. Or assignment number A3_5 and A3_6, tasks for week 8. Course overview. Introduction. Design pressure. Design temperature. Weld joint efficiency. Allowable stress. Corrosion allowance. Guideline for Tutorial 1 and Tutorial 2. Introduction. Pressure vessels are designed to work by reaching the level of pressure required to make an application function, like holding air in a scuba tank. They can deliver pressure either directly through valves and release gauges, or indirectly via heat transfer. Potential pressure levels range from 15 psi up to around 150,000 psi, while temperatures are often above 400 degrees Celsius (750 degrees Fahrenheit). A pressure tank can hold anywhere from 75 liters or 20 gallons to several thousand liters. Design pressure P. Design pressure is the maximum internal pressure in SIG that is used in the mechanical design of a pressure vessel. For full or partial vacuum conditions, the design pressure is applied externally and is the maximum pressure difference that can occur between the atmosphere and the inside of the pressure vessel. Some pressure vessels may experience both internal and external pressure conditions at different times during their operation. The mechanical design of the pressure vessel in this case is based on which of these is the more severe design condition. Design pressure P refers to the maximum pressure set at the top of the vessel, and its value is not lower than the working pressure. Both the design pressure and the corresponding design temperature are usually used as the condition of the design load. Design temperature. The design temperature of a pressure vessel is the maximum fluid temperature that occurs under normal operating conditions, plus an allowance for variations that occur during operation. Temperature affects material strength and, thus, its allowable stress, regardless of the design pressure. The strength of metals decreases with increasing temperature, so the maximum allowable design stress will depend on the material temperature. Weld joint efficiency, E. Weld joint efficiency, E accounts for the quality of a welded joint and for the concentration of local stress. This higher local stress is due to local material or structural discontinuities. The strength of a welded joint will depend on the type of joint and the quality of the welding. The soundness of welds is checked by visual inspection and by non-destructive testing or radiography. Taking the factor as 1.0 implies that the joint is equally as strong as the virgin plate. This is achieved by radiographing the complete weld length and cutting out and remaking any defects. Allowable stress, S. Maximum allowable stress is the maximum stress that may be safely applied to a pressure vessel component. The maximum allowable stress includes a safety margin between the stress level in a component due to the applied loads and the stress level that could cause a failure. The higher allowable stress values should be used only where slightly higher deformation of the component is not in itself objectionable. Example for shell and head sections. Tables in the ASME Code Section 2, Part D contain the maximum allowable tensile stresses of materials that are acceptable for use in ASME Code Section 8 pressure vessels. Corrosion allowance, CA. Corrosion is the deterioration of metals by chemical action. A material's resistance to corrosion is probably the most important factor that influences its selection for a specific application. The most common method that is used to address corrosion in pressure vessels is to specify a corrosion allowance. A corrosion allowance is supplemental metal thickness that is added to the minimum thickness that is required to resist the applied loads. This added thickness compensates for thinning, i.e., corrosion, that will take place during service. Tutorial 1, Assignment A3_5. The geometry and design data of a vertical cylindrical pressure vessel are specified. Cost estimates are being prepared for this vessel. It is your job to estimate the required component thicknesses. What are the minimum required thicknesses for the two cylindrical sections? For the same vessel, what are the minimum required thicknesses for the top and bottom heads? Design information. Design pressure, P equals 250 sig. Design temperature, T equals 700 F. Shell and head material SA515 GR60. Corrosion allowance equals 0.125 inch. Both heads and seamless. Shell and cone welds are double welded and spot radiograph. Vessel and vapor services. Cylinder dimensions shown are inside diameters. What are the minimum required thicknesses for the two cylindrical sections? For the same vessel, what are the minimum required thicknesses for the top and bottom heads? Guideline. And what are the minimum required thicknesses for the two cylindrical sections? 1. Internal pressure of a cylindrical shell ASME code equations.
Võrduppe times redivide-bis time -0 6 timespe.
2. Shell and cone welds are double welded and spot radiograph, joint type 1. Since the welds are spot radiographed, E equals 0.85 from maximum weld joint efficiency. Pressure, P is given as 250 sig. Stress equals 14,400 psi for SA515/GR60 at 700 degrees Fahrenheit. 5. For the 6 feet to 0 inches. Shell, calculate R, including corrosion allowance. R equals 0.5 times D plus corrosion allowance is equal to 0.5 times 72 plus 0.125. T equals pressure times radius divided stress times efficiency minus 0.6 time pressure. 6. For the 4 feet to 0 inches. Shell, calculate R, including corrosion allowance. R equals 0.5 times D plus corrosion allowance is equal to 0.5 times 48 plus 0.125 equals 24.125 in. T equals pressure time radius divided stress time efficiency 0.6 time P. B. For the same vessel, what are the minimum required thicknesses for the top and bottom heads? Since both heads are seamless, E equals 1.0. Weld joint efficiency, full radiograph, find E. Both heads are double welded and joint type 1. Top head, hemispherical head, ASME code equations. R equals 0.5 times diameter plus corrosion allowance is equal to 0.5 times 48 plus 0.125 equals 24.125 in. T equals pressure X radius divide 2 time S time E 0.2 time P. 3. Bottom head, 2:1 semi-elliptical head, ASME code equations. D equals D plus CA equals 72 plus 0.125 equals 72.25 in. T equals pressure times radius divide 2 times stress times efficiency minus 0.2 time pressure. Tutorial 2, Assignment A3_6. The upper cylindrical part of the vessel shown in figure has a 120-inch, 3050 mm inside diameter, type 1 butt welds, and a corrosion allowance of 0.125 inch. The design temperature is 800 degrees Fahrenheit and the design pressure is 150 psi. The material is SA-516 grade 70, and full radiography will be performed. Find the minimum thickness of the section. A. With the inside radius corrected for the corrosion allowance and B. Without the correction. C. Longitudinal stress or circumference joint. D. Maximum allowable working pressure. Guideline, use code UG-27 formulas the allowable stress in Part D of Section 2, Table 1A, for SA-516 grade 70. Table UW-12 states that the joint efficiency for a fully radiographed Type 1 but joint is P is less than 0.385 SE and T is less than or divide 2. Circumferential stress, longitudinal joint. Where P design pressure, UG21. R plus CA equals inside radius plus corrosion allowance, UG16 and UG25. S equals maximum allowable stress from Section 2, Part D for SA-516, grade 70 at 800 degrees Fahrenheit. E equals joint efficiency for a Type 1, fully radiographed longitudinal joint in a shell. From Table UW12. A. Inside radius corrected for the corrosion allowance. T equals pressure time radius divide stress time efficiency 0.6 time P. TREQ equals T plus CA. B. Inside radius corrected for the corrosion allowance. T equals pressure time radius divide stress time efficiency 0.6 time pressure plus corrosion allowance. TREQ equals T plus CA. This variation requires that the plate be 0.881 inch thick or thicker. The thickness of 0.756 inch is required to resist the pressure. The designer would most likely select a 1-inch thick plate for the construction. C. Longitudinal stress. T equals pressure time radius divide 2 times stress time efficiency plus 0.4 time P. Where P equals design pressure, UG21. R equals inside radius. S equals maximum allowable stress from Section 2, Part D for SA-516, grade 70 at 800 degree F. E equals joint efficiency for a Type 1, fully radiographed longitudinal joint in a shell. From Table UW12. D. Max allowable working pressure. T equals T nominal minus CA. T equals 1 inch. 0.125 inches. T equals 0.875 inch. Use the second part of Formula 1 in UG 27. P is less than 0.385 SE and T is less than or divide 2. P equals S time E time thickness divide radius plus 0.6 time thickness. Pressure plus stress time efficiency time thickness divide radius plus 0.6 time P. End of slide. And thank you for your attention.